Okay, so I think it's 10:05, a number of people slowly converging to a number of seats available in this room. Yeah, and so, okay, my name is Dennis, and today I would like to talk about my favorite feature of Scala, and this feature is string interpolation. Many of you probably know already about it, but I only use it as default string interpolator called S. But not many of you know that this actually isn't really, this feature isn't really about strings at all, and the name is extremely misleading because, in fact, it lets you embed arbitrary languages in Scala. And, for example, quasiquotes introduced in 2.11 are an example of a language embedded this way. And this is why I would like to call this feature, like I personally like to call this feature extensible a quotation syntax rather than a string interpolation, because it's really not about strings and it's really not about interpolation. And let's have a look how it actually works. So this syntax is really just about a syntactic sugar that is extensible by a user. So under the hood, when you write a Q hello name, what compiler sees is this call to a method on a string context. It doesn't have to be there by default, like in standard library. You can also extend it as an implicit class, and it will happily find it for you and use it for your own good. And once you, as the library, are in control of execution, you can do pretty much whatever you want. You can return arbitrary types, and nobody will stop you. It's not. You don't have to return strings because it's really that's it. So whatever you do in a method, it's up to you. You can connect to database or like do lots of weird stuff. And to define your own quasiquote or a quotation, you just need an implicit class with an apply inside of it. And from here, it's pretty much a blank canvas. And today, we would like to fill it with a small example of embedded language. And this language is called Joy. So Joy is a functional stack-oriented programming languages. And unlike many popular languages, it's stack-based. It means that every operation implies operation on stack. So, for example, when you say 1, 1 plus, it means like put 1 on the stack, and the stack becomes 1. Then put another 1, and you'll have 1 and 1. And then add the last 2. And there is a number of built-in operators, of course, to make it easy to write actual meaningful code. But the nice concept is that every program, program a composition as text is actually equivalent to a function a composition. And even if it looks a bit imperative, like say like push a number there, it's not really like that, because it can think of numbers as functions that are composed by like one another. And except for primitives, Joy also has this quotation brackets, and you can really think of them as closures. Instead of evaluating a quotation instantly, it just pushes it on stack as literal, and you can invoke it with default I operator. Also, quotations are used as a collection type in a sense, so you have first and rest in most functional programming languages. And a nice example of how it's functional is that everything is basically implemented as a quotation, like as a usage of quotation. For example, map on collection just uses like first quotation as list and a second one as a closure that does some stuff over it. And it's really nice. So what we would like to do today is to embed this language into Scala in a seamless way, so that like you can write your programs in Scala, but at the same time use this nice syntax. So first, we would like to define an AST for our language, and overall it's pretty simple. So you have 3 like value classes like int, bool, and names that define a values on stack. Name isn't really a value, but more like something that will be resolved to default function like equals. And quoted is a representation of square bracket stuff, and a program is an AST for the whole program. So once we have AST, we can also define is the way we parse code into ASTs. And for that, we just use default parser combinators, but pretty much any library will do here. I'm just using it here because it's one of the more popular ones because it's covered in books and stuff like that. But you can really use pretty much anything here, like it doesn't matter. And as you can see, syntax is really simple. So you have ints, names, true, false, and quotations, default operators. Like under those triple dots, there are some ugly regular expressions, but I don't really want you to see those. But yeah. Okay, so we have a parser, and we can define our first version of a quotation. And all it does is it takes first a part out of the context and parses it. Yeah, and yay, we got our first executable interpolator, and it works. But as you can see, it's not really nice because case classes don't really have this like a weird pretty print, and we would like to have something more resembling our language. So we define a toString on our root type, and now our programs are pretty printed as they are. So a next step, like right now, all of the work is done at runtime. So even though we statically know the shape of a tree that will be produced is still done at runtime, and it's not really cool. We would like to abuse a macros a bit and make it work at compile time instead. So we define a macro. So overall, it's pretty much the same stuff. So on top, you have a signature of our interpolator, and on the bottom, you have actual code that's being executed. And as you can see, it's pretty much the same stuff, .parse.get, but also we have this lift function, and what it does is pretty much converts value to a representation of that value as a Scala tree. And yeah, that's pretty much it. And now, yeah, and one more thing is also we need to parse macro application where quasiquotes to get parsed on ours, which were previously available as runtime values. So now we have the same quotation working for us at compile time. So instead of at runtime parsing this string every time, we parse it once when macro expands, and it has been replaced by an AST that represents the snippet. Pretty cool. So as of now, we have like 0 overhead because all the stuff is sugared away into underlying primitives. But as it is now, it's not really composable, and we would like to compose trees out of smaller parts. And this kind of a composition is called unquoting. So you have big quotations and like dollars inside, and each dollar is unquote. In string interpolation terms, it's called splicing, but in quotation terms, splicing means something different actually. So to implement it, we need to patch our heck a little bit and parse not just the first part, but all of the code. And to do that, we join all of our parts and fill in holes between them with a special marker. And this marker will let us know like at which places do we have to substitute stuff. So as of now, it will work something like this. So when you say $2, $2, it will replace those with markers, and you can clearly see those here. But this is not what we actually wanted, and we would like to replace every marker in our tree with an actual input that was given by a user. So what we do is we tweak our lift function a tiny little bit, and say when our name is basically a marker name, we take a user input rather than like a typical path. So now it works, and now macro can expose simple composition, and it's cool. And we can like compose a larger programs out of smaller parts. But wouldn't it be cool if instead of like using a J-quote for each and every value, we were just able to use Scala values and just put them in right in and make it just work? And to do that, we need some way to map Scala values onto their representation in Joy. And to do that, we define a type class, which is basically just a function from t, arbitrary type, to Joy. So whenever an implicit value of this type is available, it means that when you put it into quote, it needs to be converted this way. And in our object, we also have a number of default instances, like we would like ints to be lifted as Joy ints, and do stuff like that. So another change we need to do is we need to tweak a signature a little bit, because previously our arguments could only be Joy values, but now it's like pretty much anything. And like it would have been easy to use just any, but any in signatures and macros don't really work very well, because when a compiler sees any, it thinks like, oh yeah, I will do a lazy work and wouldn't really infer everything, and I just you know, have inferred a type set to any, and it will not work for us because we really need specific types. And if we put just this dummy type argument there, it will all work out together. And also, we need to tweak our lifting a little bit, like lifting from Joy value to a Scala tree. We need to, instead of using arcs of I everywhere, we will do a bit of magic and look for implicits in our scope. And this can be done with infer implicit value. And to pass something to infer implicit value, we need to first construct a type, and we do that with applied type stuff. Yeah. And once you have a value, we use this function as a converter, and that's pretty much how it works. So now we can actually put arbitrary values into our Joy quotes, and this is really cool because we can this way we can also define like a complex representation of complex data structures in Joy, and like have a seamless interop in one way. Another feature we would also like to have is a way to abstract over a number of elements. So with a $foo, we can say like $bar, but we can not say $foos because it's like arbitrary length. And for this, we need extra feature called splicing. And what splicing does is it flattens the value into the positions. For example, we would like to flatten a list of ABC into a quote and become an ABC plus quote. And to do that, we tweak our macro again a little bit. So as you remember, we have this lift function for Joy values, but we also need to customize how Joy lists, like inside of quoted and program, are converted to a list in Scala trees. And to do that, we parse it and like look for this dot dot. And when we see dot dot, we need to do a bit of extra work and like have a bit nicer tree that composes well, but it pays off overall because now this actually works. So now the hard part, feature interaction. So we have splicing, and we have and splicing expects iterables to be put in that position. And to make it work with Joy programs, so that you can flatten Joy programs as collections, the easiest way to do it is to make a quote and program iterable. And that's simple, but it also like improves our composability a little bit. Yeah, so it works. Okay, another feature interaction. So what about using splicing and lifting together? Like, what if you have a lift of int, but we would like to splice a list of int? So this is like a corner case we didn't cover before. So we need to tweak our macro a little bit again. And it gets a little bit involved, but overall the idea is if you have like this a dotted flag, all it does it knows if we're having a list of t or t. And if you have a list of t, we need to have a map other than a function application. And that's pretty much how it works. And also an important part is like here we use iterable of t. Like we look look up implicits not just by argument type, but by a nested type. So this way, so here we have a list of int. We need to look up int, not a list of int. And to do that, we need to extract a type of iterable as if our type is iterable. And for this, we have this wonderful async_throw default function that takes two symbols and type. And from here, we can say that, like, if we look at iterable type parameter from a concept, from a context of our type, how will it look like? And in this case, like a list of int, like will have iterable type param as int. So yay! So now not only can we lift separate values, but also we can lift a list of values. So a feature interaction. So far we have an AC, we have parser of that AC, we have compile time quotations that are pretty composable, but they're only work in expression mode for now. We also have unquoting and higher order dot unquoting, and we also have a type class to interop. So it's pretty good already, but it's not enough. And the missing part is really pattern matching. So because in pattern matching, everything is very similar, but a bit like slightly differently. So and it works slightly differently. So our macro needs to handle it. So right now, if we just put our J quote in a pattern context, it will not work because J doesn't have an unapply, and this really confuses everything. So what we do is we just add an apply as another entry point, and we in our macro we have a single implementation, but two entry points that dispatch at the same one. And cool, now it actually works. So it wasn't really a lot of work, but we needed to tweak it a little bit. But what about, again, feature interaction? What about unquoting? Oops, doesn't really work yet. Okay, we need to fix that. So an interesting part about macro expansion in pattern mode is the way you don't really expand, like in expressions, your expression is written with new expression, but in pattern mode, you cannot really rewrite all pattern. You rewrite only like if you say case foo of x, you can only rewrite foo part. You cannot rewrite x part. So you need to expand into another extractor. So in a sense, your macro like expands into extractor that then matches the value. And to do that, we just have this new anonymous new with unapply, and this new will be a domain specific, like this quote specific matcher for our quotation. And also, we need to tweak our arc function so that it produces pattern bindings, but not expression bindings. And now, yay, it actually works. And this is pretty cool. So again, we didn't have to do much work, but a little bit of tweaking to get the balls rolling. So what about splicing in pattern mode? Pretty much this is how you expect it to work, and it actually does work without any further tweaks because it was like kept in mind in the very beginning. But yeah, if you're interested, like look at the source code, how it actually works. It's pretty funny. So another feature interaction is what to do with lifting in pattern mode. So in expression mode, we relied on a type of value, but in patterns, we don't really have types because everything is evaluated not from bottom to top, but from top to bottom. So we need some way for user to define that he needs a value of some specific type in that place. And we use ascription syntax here. And to implement it, we also need another type class for a conversion as the other way around. And there is a bug here. It should really say unapply because it's really important because the way pattern matching works, we want our unlifting values actually be extractors, so it has to be unapply. So what we do is a very similar stuff as what we did in expression. We look up an implicit value, and that's it. And we compose it as a pattern. There's a tiny little bit a difference in how we handle arguments. We need to use this C internal subpatterns, but that's like implementation detail. But yeah, so now it works. Cool. Another feature across is working, and another interaction is splicing, unlifting, and pattern matching. And yeah, it's you can make it work, but I will include it here. So overall, right now we have a quotation that works as pattern. It works as expression. It has 2 modes of unquoting, and it has 2 type classes for interop. And you might have already noticed, but we have tested all interactions between all these features, and it's really important because when you meet something, it might just explode in a face of your user, and it's really important to have a tool that works flawlessly no matter how you use it. So in this case, we have 8 possible modes of interaction, but all of this is handled. So we're pretty much done with our quote. Let's do some coding with it. So Joy programs are really simple in their semantics. Whenever you see a value, look up a value in symbol table and return it as a function. Whenever you evaluate a whole program, you evaluate each of its elements and compose it as function. And when you see a value, just push it onto a stack. That's pretty much all of the Joy evaluation you really need to know about, and that's eval. And an interesting part here is evaluation of Joy program isn't a value in a sense like int, but it's a value from stack to stack. It's like a function. So program itself is not a mutable entity. It doesn't mutate anything. It's just an express of your intent, what you wanted to do. And in this sense, it's purely functional. And now let's implement some default primitives. And now we can finally use our quotation to do some fun stuff. So each of the rows in this table defines a mapping from a default primitive available in a language, like default operation. And then we have this 2 quotes, one as a pattern and one as an expression. And here, what you basically see is AST rewriting with quotations. And this is basically the perfect use case. As you can see, it's a very high level. It lets us directly use Scala values, like, for example, on right-hand side of equals. We don't need to do any magic. It just does the right stuff. And we can also use types, we can also request specific types, because we have unlifting and lifting, and we can request Boolean, and then perform operation on it as a Scala value, and then put it back, and it will all just work because we have lifting and unlifting. There is also a number of other primitives I haven't shown you before, but they're all there. And now it's time for a short demo. So here's the REPL where we have our environment set up. So we have our JQuote that we have just developed. And we also have eval on it. So what eval does, as I told before, it doesn't really return a value, it returns a function. So to make it all work, you need to pass a stack. And a stack, in our case, is represented as a quotation. So like empty quotation is empty stack. Okay, so let's do some evaluation, like say 1 plus 2, like simple stuff. Okay, that's cool. So what happened here is we first we first converted our program to a function with eval, and then we passed an empty stack to it, and magic, it works. That's pretty cool. Okay, maybe a little bit bigger. Okay, so now let's do some funny stuff. What about like functional primitives I've been talking to you about? So let's do a map and a quotation. So let's say we have a list and we would like to multiply everything by 2. So this is what we might write. And the way it works is Joy will take each and every value from a list, and for each value it will execute a second quotation in that context. So for example, when we get to multiply 2, it will work in context like 1, 2 times, and we get a new list where everything is multiplied by 2. And this is really cool because here, as you can see, we don't have any intermediate values, and this is actually a beauty of stack-based programming languages, because that you don't really need those most of the time. Another example where you don't really need intermediate values is a recursion. Let's implement a simple a factorial function. So let's say we want to know what's the value of 5 factorial, and it's a bit weird, but this is how it works. Again, non-intermediate values, because stack-based is awesome. Okay, so the way it works, you have a default primitive recursion, a combinator, and what it takes 2 quotations. And the way it expanded, it does recursive rewriting. Is that at first, when you call a prime rec, it will take a quotation out of stack, so it will be just 5. Then it will have a look at 5. If 5 is 0, it will execute first one, and if it's not, it will put a 5 minus 1, 4 on the stack, and then put times into squared. And how it will work out is that this will all evaluate into something like this. So this will evaluate into 120 because it actually does a recursion without any local name being in. And if we want to visualize it a bit, so it will expand into something like this in the end, and it will return the right result. Okay, so now we're pretty much done here, and I would like to outline again. It's so easy to just do rewriting on trees once you have quotations. This code looks so much uglier without them, and what you had to do is like do type checks and like convert from Joy values to Scala values, and like it lists lots of code that wasn't really needed. So to sum up, so we embedded a language as a quotation, and it was, in my opinion, it was a really awesome experience because now we have a first class like literal for our language, and it has a very type intro with Scala, and I think, and we can do a really cool rewriting with it. The second lesson I would like to outline is that feature interactions are really hard. No matter what you do, if it's a quotation, programming languages, or a simple library, you need to test all possible combinations, because when you miss some stuff out, it explodes in your face. And you really need to explore all the space, because if you don't explore it, then it means that your users will have to explore it for you, and it usually means an unpleasant experience. And lastly, I'd like to acknowledge this. This presentation had a lot of macros stuff, and it might have been a little bit dense, but this is only a problem of a current framework, and we're working on making it better. And if you want to know more, come to Zenabized talk today and to see what we have to offer in macro world. So thank you.